This video goes over geometric distributions. In some situations where otherwise the binomial distribution applies, we are interested in the probability that the first success will occur on a particular trial, as opposed to a number of successes and a number of failures that are going to occur in a particular value of n trials. So the probability of success after waiting a time of x failures is given by this expression here. So the probability of success after a waiting time of x failures. So just like the binomial distribution, our exponents have to add up to our number of trials. In this case, our exponent on the p is always going to be equal to 1. So in a geometric distribution, you have two outcomes only, success or failure. Independent trials. The probability of success remains constant between trials, and the experiment is repeated until a success occurs. That signifies the end of the experiment. So for example, when taping a television commercial, the probability that a certain actor will get his line straight on any one take is 0.4. So this is our probability of success, which means that our Q value is 0.6. Find the probability that this actor will get his line straight for the first time on the third take. So that means 2 failures, 1 success. So I would express my probability as the probability that he gets it right on the third take is 0.6 squared, those are the 2 failures, times 0.4 to the 1 for 1 success, which is going to give me a probability of 0.144. The probability that the actor gets it correct on the 4th take is going to be 0.6 cubed, so 3 failures, and then 0.4 to the 1, so 1 success, and this would give me a total probability of 0.0864, or about 8%. The last example would be the probability that he gets it correct on the 5th take. So I would have 4 failures, 0.6 to the 4, times 0.4 to the 1. These two add up to my total number of takes. I have 4 failures before I have 1 success. Multiplying these together will give me 0.0518. And if you notice, these 3 values look like the beginning of a geometric series. So I have a r squared, a r cubed, and then a r to the 4th. So that looks like the beginning of a geometric series there. Let's do one more example. A poll indicates that 34% of the population agrees with a recent policy that the government has adopted. Find the probability that the pollster wouldn't find a supporter of the policy until her 6th interview. So that means 5 failures, 1 success. So I would find my probability for the 6th interview would be my probability of failure, which is 66%. I have 5 failures, and then I have 1 success, so 34% chance. Multiplying those together is going to give me approximately 0.0426, or about 4%. So just going back to the question, I've got 34% is my probability of success. Q is 1 minus P, or 0.66. In this question, we're also asked to calculate the expected waiting time before the pollster finds someone who agrees with the policy. For a geometric distribution, this is our equation to find the expected value. So my expected wait time is my Q value 0.66 over my p-value, 0.34, and it tells me approximately 1.9 people. So I'd be waiting anywhere between 1 and 2 people to find someone who agrees with the policy. Those are 2 examples of the geometric distribution. Remember that the exponent always has to add up to your total number of trials. Your success signifies the end of the experiment. That is the key descriptor of the geometric distribution, that you are waiting until you get 1 success.